All right, diving in today. Energy-based models, EBMs. Got a whole stack of research here, a white paper on how they're shaking up security, some classic stuff from the AI giants, Jan LeCun, Jeffrey Hinton, the big names. Even some fresh off the press case studies
Yeah.
using EBMs to actually catch bad guys.
Yeah, it's really interesting stuff. For ages, security's been all about here's the good stuff, here's the bad stuff, train the AI to spot the difference. But the bad guys, they don't play by the rules, right? They're always changing things up. So we need something new, something that can handle the unexpected. And that's where these EBMs come in. They're all about modeling uncertainty in a way that other AI just doesn't. It's a whole new way of thinking about it.
All right, so uncertainty, that's the key word here, right? We're dealing with the unknown. But before we get too deep into that, what exactly are these EBMs? How are they different?
Okay, so at the core, it's all about energy. It's kind of like imagine the model's looking at a piece of data and it's trying to decide how comfortable it feels with it. Low energy. That means, this looks familiar, this seems normal. High energy. Uh-oh, something's not right here, this is weird, this could be a problem.
So instead of telling the AI, this is good, this is bad, we're teaching it what feels right, what feels wrong.
Yeah, exactly. It's like instead of memorizing a list of bad guys, it's learning the shape of the good guys, and anything that doesn't fit that shape stands out. Like Jan LeCun, he's one of the pioneers of this whole EBM thing, and he describes it as learning to associate these energy scores, these comfort levels, with different data patterns. So say you're looking at network traffic, and the model gives you a really high energy score for a certain packet. That's a red flag. Something unusual is going on there.
Got it. But how is that different from, just training a regular neural network to tell you if something's malware or not?
So a traditional neural network, it learns a direct connection, input to output. You show it a file, it says malware or not malware. But EBMs, they're going deeper. They're learning the structure, the relationships within the data itself. They don't need to see every single type of malware to know that something's off. They're like, wait, this doesn't fit the energy landscape of normal behavior. Something's wrong here.
So it's not about memorizing a list of threats. It's about understanding what normal looks like and then spotting anything that deviates from that.
Precisely. And this is also what sets them apart from those generative models, the ones that are all about creating new data based on patterns. Generative models, they want to make new stuff that looks like the old stuff. EBMs, they're more about understanding the essence of the data, how the pieces fit together. And then, probabilistic models, they focus on how likely something is. But EBMs, they take a different approach. They give you this energy score, which tells you how compatible something is with the model's understanding of normal without needing a full probability breakdown.
Okay, so it's like this energy map, right? Familiar stuff is down in the valleys, low energy, comfortable, and then anything unusual that's up on the peaks, high energy, alarm bells going off. And the white paper we looked at, it mentioned that EBMs are good at handling all sorts of data, structured, unstructured, the whole shebang. Why is that so important in security?
Well, because in security, you're dealing with a mess of data, right? It's not all neat and tidy. You've got your system logs all structured and organized, but then you've got threat intelligence reports, emails, even code. EBMs, they're not picky. They can handle it all. Because they're focusing on these underlying relationships, how the pieces fit together, they can spot patterns, anomalies across all these different data types without needing to treat them completely separately.
That's powerful. So EBMs are all about learning this energy landscape, figuring out what's normal, what's not. Now, let's get into that uncertainty piece. What are their strengths? What are their limitations when it comes to modeling the unknown?
Well, one of the biggest strengths of EBMs is exactly how they use that energy function, that comfort level, to show you how well an input fits with the expected output. It's not just a yes or no, it's not just a probability, it's this energy score that tells you, hey, this input, it's kind of out there, it doesn't quite fit with what I've learned. And that score, that's a way of representing uncertainty. A high energy score, that means I'm pretty sure I haven't seen anything like this before. This is unusual.
So a higher score, more energy means the model is less certain.
In a way, yeah. It's like the model saying, this is way out there, this doesn't match the patterns I've seen, and that's really useful for anomaly detection. Anything that comes up in those high energy zones, that's a potential red flag.
Right, so we're looking for those peaks on the energy landscape. Now, I remember reading about something called Products of Experts by Jeffrey Hinton. How does that fit into all of this?
Oh, yes, products of experts. That's a really neat idea. Basically, it's a way of modeling really complex stuff by combining the opinions of a bunch of simpler models. Think of it like a team of specialists, each one looking at a different aspect of the data.
So it's like a panel of experts, and they're all giving their opinion on whether something is normal or not.
Exactly. And each expert, they're assigning their own energy score based on what they see. Now, the overall energy, it's only going to be low if all the experts agree, if they all say, yeah, this looks fine to me. If even one expert is like, wait a minute, something's not right here, the overall energy goes up.
It's just like an alarm system. It only goes off if everyone on the team is feeling uneasy.
Exactly. And this makes it really good at finding those subtle anomalies, the things that a single model might miss. Like in cybersecurity, you could have different experts analyzing different parts of the system, network traffic, user behavior, whatever. And only when they all agree that something's fishy, then you trigger an alert.
That sounds way better than having a bunch of false alarms going off all the time. Now, what about EBGANs? Energy-based generative adversarial networks. That was another one that caught my eye.
Yeah, so EBGANs, they're a really interesting combination of energy-based learning and GANs, those generative adversarial networks that are all the rage these days. So you know how in a regular GAN you've got a generator trying to create fake data and a discriminator trying to tell the real from the fake?
Right, they're like playing a game, constantly trying to outsmart each other.
Exactly. Now, in an EBGAN, the discriminator, it's not just saying real or fake, it's acting like an energy function. It's learning to give low energy scores to real data and high energy scores to the fake data.
So it's like the discriminator is saying, this feels real or this feels fake based on the energy it's sensing.
Yeah, that's a good way to put it. And the cool thing is, because it's trained this way, the EBGAN can learn really complex patterns. And for security, that means it can spot those anomalies, those things that just don't fit the normal energy profile. Like if the EBGAN discriminator gives something a high energy score, that's a sign that it's probably different from the real data it was trained on.
So it's good at finding the outliers, the things that break the mold. Now, all of this sounds pretty impressive, but are there any drawbacks? What are the limitations of EBMs?
Well, like any powerful tool, they come with challenges. One thing is they can be computationally expensive, especially as they get more complex and you're dealing with lots of data. Learning those energy landscapes, it takes a lot of processing power. And like many deep learning models, they need a good amount of data to learn effectively. You need to show them enough examples of normal behavior so they can figure out what's unusual.
Right, so lots of data, lots of processing power. That makes sense. But okay, we've talked about the theory, now let's get practical. Why should our listeners care about EBMs? Where are they actually making a difference in the real world?
Well, the research shows that they're already making a big impact in cybersecurity, solving some real problems, like, for example, detecting anomalies in network traffic. There was a study in IE transactions on information forensics and security back in 2022, and it showed that EBMs were actually better at spotting malicious activity than traditional neural networks. And a big reason for that was their ability to directly model the energy of those unusual traffic patterns, which meant more accurate detection and fewer false alarms.
Fewer false alarms. That's music to any security analyst's ears.
Absolutely. And it's not just network traffic. At the RSA conference in 2023, there was a case study on using EBMs to prioritize security incidents. Basically, they modeled the different characteristics of an incident as an energy landscape, and the higher the energy, the more critical the incident. This allowed them to quickly and accurately assess the severity of an incident, even with limited information.
So it's like a triage system, helping security teams focus on the most urgent threats.
Exactly. And this approach is also being used for vulnerability management. At Black Hat 2024, there was a presentation on using EBMs to predict how likely a vulnerability is to be exploited. By modeling the uncertainty in attacker behavior, they were able to prioritize which vulnerabilities to fix first, which is a huge help when you're dealing with limited resources.
That's way more sophisticated than just relying on those CVSS scores.
Right. And it gets even more interesting. They're even using EBMs for strategic risk management and business continuity planning. There was a study in IE Security and Privacy in 2023 that showed how you could visualize cybersecurity risks as energy landscapes. Stable, low-risk situations would be in the valleys, while unstable, high-risk situations would be on the peaks. This can help organizations make better decisions about where to focus their efforts and how to recover from incidents.
So EBNs are being used everywhere, from analyzing network traffic to planning for disaster recovery. That's pretty impressive. Now, for our listeners who might be new to this whole energy concept, is there a metaphor we could use to make it a little more concrete?
Sure. Imagine you're trying to teach a model what a perfect apple looks like. You show it a bunch of perfect apples and it learns the shape, the color, the texture. Now, if you show it an apple with a bruise, that's going to have higher energy because it deviates from the model's understanding of a perfect apple.
Okay, so the bruised apple stands out because it doesn't fit the mold.
Exactly. And this relates to how autoencoders work, which are a type of EBM. An autoencoder tries to reconstruct the input data. If it can't reconstruct it perfectly, that means there's an error, which translates to high energy.
So the reconstruction error is like the energy. The higher the error, the more unusual the data.
Precisely. Now, one question people often have about these complex AI models is, can we trust them? If we don't understand how they're making their decisions, how can we be sure they're right?
Yeah, that's a valid concern. It's like, how can you trust a black box?
It's a fair point, and it's something researchers are actively working on. There are techniques being developed to make EBMs more transparent, to help us understand why they give certain energy scores. One approach is feature attribution, which highlights which specific features in the data were most influential in the model's decision. And visualizing the energy landscape itself can also give us some insights into what the model considers normal and where the anomalies lie.
So while they might not be perfectly explainable yet, we're making progress in understanding how they work.
Exactly. And the benefits we're seeing, like the dramatic reduction in false positives, often outweigh the current explainability challenges, especially with these new interpretability techniques emerging.
Well, this has been a fascinating deep dive into energy-based models. It sounds like they offer a really powerful and fundamentally different approach to understanding data,
Yeah.
especially when it comes to dealing with uncertainty, which is so crucial in cybersecurity.
Absolutely. And as we've seen, they're not just theoretical concepts. They're being applied in very real and impactful ways to tackle some of the toughest security challenges.
Before we wrap up, any final thoughts for our listeners?
Just to reiterate, while EBMs are incredibly promising, there are still some hurdles to overcome, but their potential to uncover those unknown unknowns, the threats we haven't even thought of yet, makes them a technology worth keeping a close eye on.
Absolutely. And on that note, here's a final thought for our listeners. Think about how this concept of energy, this idea of how well something fits, how stable it is, could be applied outside of cybersecurity. How could you use it to understand complex systems in other fields? It might just spark some new ideas. And for those of you who want to dive deeper into the technical details, be sure to check out the research papers and the white paper we've mentioned today. Thanks for joining us on the deep dive.